Section 7.4, area of a triangle. Now, of course, it's true that given a triangle, if we know the height, where this is some right angle, and we know the base width, then the area of a triangle is of course going to be 1/2 the base times the height. That's absolutely true, and that's not changing here. But the situation that is occurring is that just like in the previous sections we had triangles that did not have right angles, if we have a limited amount of information, I claim that we can generalize the area of the triangle, specifically any triangle, and say that the area K of any triangle is 1/2 of the product of the lengths of two sides and the sine of the included angle. And so if you wanted to prove this, all you would have to do is take that triangle like I did here, use the labeling that we did when we talked about sines, law of sines and law of cosines, superimpose this height, and then you could work from there and you could find these formulas. Let's say we want to find the area of the triangle for which B is equal to 8, C is equal to 5, and angle A is equal to 40 degrees. And if you need to, sketch the triangle real quick, label angles A, B, and C as capitals, and then the opposite sides are the lowercase. And so there's our triangle. Notice that B being 8, C being 5, and A being 40 degrees gives us exactly what's necessary to be able to calculate the area. Therefore, our area K is equal to 1/2 the two sides trapping the sine of that angle. And so that's going to be 8 times 5 times sine of 40 degrees. Then if we do this calculation and round it to 2 decimal places, I get that this area is approximately, rounded to 2 decimal places, 12.86. And so there we have it. That's the area. Whatever the units are, it's always going to be square units. So just make sure that you recall that whatever the units are, it's squared when we discuss it in area. Alright, but then we get this other formula for when we have side, side, side. So recognize that that area of a triangle formula that we used a moment ago is directly connected to a side angle side triangle. Well, now if we have a side, side, side triangle, then I claim that we can find the area to be the square root of S times S minus A times S minus B times S minus C, where S is this thing called the semi-perimeter, and S is 1/2 of A plus B plus C. Let's try it. So, if we're trying to find the area of a triangle for which A is 9, B is 6, C is 4, we need to find two things. We need to find this thing called the semi-perimeter. And so S is equal to 1/2 of the sum of the sides. So 1/2 of 9 plus 6 plus 4. I get that it's 19/2. I don't want to round yet because I don't want to create error. Well then, my area formula is going to be equal to the square root of the semi-perimeter times the semi-perimeter minus A, which is 9, times the semi-perimeter minus B, which is 6, times the semi-perimeter minus C, which is 4. So it's just the square root of the semi-perimeter times semi-perimeter minus each side, all multiplied together. Alright, well, then calculator value. And I get that this is approximately 9.56. Since we don't know whatever the unit is, we know that it's just whatever our unit is squared. Alright, so now a painter needs to cover a triangular region with sides of 40 feet, 50 feet, and 46 feet. If each can of paint covers 175 square feet, how many cans of paint are needed? So specifically, this is just an application problem where first we find the area, recognizing that this is a side, side, side triangle. Therefore, we need to use Heron's formula just as we did a moment ago. So the semi-perimeter is going to be equal to 1/2 of the sum of the sides, 40 plus 50 plus 46, which I get to be 136 over 2, or 68. So no approximations at this point. Then Heron's formula tells me that my K is going to be equal to the square root of the semi-perimeter times semi-perimeter minus each side. So minus 40 times semiperimeter minus 50 times semiperimeter minus 46, all square rooted. And I get that the area of this triangle, or this triangular region being discussed, is 868.32 feet squared. Well, then the question becomes, if each can of paint covers 175 square feet, how many cans of paint are needed? And so if the coverage is 175 square feet, we really just want to know how many cans will it take to cover this. And so I claim that the number of cans needed is going to be equal to 868.32 divided by 175, which I get to be 4.9, which really is going to round up because of course we can't buy partial cans. And so I'm going to say that it's going to take at least 5 cans of paint. Now if they wanted some decimal representation, that would be fine, but at some point recognize that we're thinking about purchasing, and I'm thinking about whole cans of paint. Alright, now we want to find the area of the segment shaded in blue in the figure. So notice that I have this shaded region, right? And so this shaded region, just brighten it up a little bit for us, is the specific region that I'm trying to find. Well, how in the world can I find that shaded region? Well, my hint is that we already know, or we should recall, that we can find the area of the sector of a circle. And so if I want to find the area of the sector of the circle, that's everything inside that pink figure, this here. And then I can subtract the area of this triangle. And if I subtract this area of the triangle minus that whole sector, if I take that sector minus that area of that triangle, we will have the answer to our shaded region. And so I'm just going to call this shaded region B, since they call it the shaded blue region. So B is my area. Well, it's specifically going to be equal to area of a sector minus the area of the triangle being described. Well, notice that this one, we know that the radii of the circle is 9. We also know that then this radii must also be 9. And since that's the case, and then we do have units, they are feet. And since this is the angle subtended by the central angle, 75 degrees, I have the central angle for my area of a sector, and I have my central angle for my area of a triangle formula. So my area of a triangle formula, that's the easy one that we just picked up, that's going to be 1/2 of 9 times 9 times sine of 75 degrees. We do need to be careful because remember that the area of the sector of a circle, the theta here is in radians, so I'm going to have to convert 75 degrees to radians, but that's easy, right? Because 75 degrees, we just multiply by one in disguise, which is going to be pi over 180, and that's going to be my answer in radians. And so I get that this reduces to be 5 pi twelfths. And so that's my radian measure of theta. So specifically it's going to be 1/2 of my radius squared, which is 9 squared, times 5 pi twelfths. Do make sure you're still in degree mode. I know that there's a radian here, but the only place we've got to worry about degree and radian mode is when we plug things into the trig function. And since we're plugging 75 degrees into sine, we need to be in degree mode. And I get that this area of section B is approximately 13.89, and we are in feet squared. The dimensions of a triangular lot are 161 feet by 124 feet by 139 feet. Side, side, side triangle. If the price of such land is $3 per square foot, how much does the lot cost? And we're going to round to the nearest penny. And for the moment, I'm just going to avoid rounding. I'm going to avoid rounding until the very end to confirm that this is okay. So, notice that since we have a side, 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 we're going to use Heron's formula. So I need to find the semi-perimeter, which is 1/2 of A plus B plus C, or 161 plus 124 plus 139, which I get to be 212. And then Heron's formula tells me that the area K is equal to the square root of semiperimeter times semiperimeter minus the first side times the semiperimeter minus the second side times the semiperimeter minus the third side. And so since that's my K, then the cost is just going to be equal to that area K times $3, which, when doing the calculation, rounding to the nearest penny, I get $25,002.13.